You are standing in a parking lot in Wyoming, and the ground beneath your feet is rising. Not much, about an inch a year in some places. You cannot feel it. Your car does not roll. The visitor center does not tilt. But scientists with GPS stations buried in the rock can watch it happen in real time. And the reason it is rising is the same reason 3 million people visit this spot every year to take photos of boiling water shooting into the sky. Underneath Yellowstone National Park sits one of the largest volcanic systems on Earth. Most people call it a ticking time bomb, but the real answer is far stranger than that. Here is what you were probably taught. Yellowstone is overdue for an eruption. Scientists are worried. Any day now, the whole thing could blow, bury half the country in ash, and end civilization as you know it. That story has been repeated so many times it feels like fact. It shows up in documentaries, in late-night television, in the group chat every time there is a small earthquake near the park. But it is almost entirely wrong. And understanding why takes you into the guts of a system so strange that even the people who study it for a living are still arguing about what it actually is. Before you go any further, it helps to understand the word supervolcano itself, because it gets thrown around so casually that its real meaning has almost dissolved. A supervolcano is not a bigger, angrier version of a normal volcano. It is defined by scale. Any eruption that ejects more than 240 cubic miles of material in a single event earns that label. For comparison, the 1980 eruption of Mount St. Helens, the one most Americans picture when they hear the word volcano, released less than 1 cubic mile of material. Yellowstone's largest known eruption released roughly 600 cubic miles. That gap is not incremental. It is the difference between a bonfire and a wildfire that reshapes a continent. Understanding that scale is part of why the myth feels so justified. The geology really is extraordinary. What gets lost is the timeline attached to it. Scale and schedule are two completely different questions, and the first one being true does not automatically make the second one urgent. Let's start with what is really down there. Yellowstone sits on top of what geologists call a caldera, a giant collapsed crater roughly 30 by 45 miles wide. It formed after a colossal eruption around 631,000 years ago, one of at least 3 enormous blasts in the region's history. Beneath that caldera is a 2-part plumbing system. Close to the surface, around 3 to 9 miles down, is a reservoir of partly molten rock. Below that, much deeper, is a second, larger zone where hot material rises up from the Earth's mantle. Together, they form what people casually call a magma chamber. But here is the twist almost nobody mentions. That chamber is not a swimming pool of lava waiting to erupt. It is mostly solid rock. Dr. Michael Poland, the current scientist in charge of the Yellowstone Volcano Observatory, has spent years trying to correct this exact misunderstanding. For a long time, researchers estimated the shallow reservoir was only around 5 to 15% molten. A newer seismic imaging study in 2025 sharpened that picture further, mapping the boundary of the reservoir directly and finding that roughly 86% of its upper portion is solid rock, with the remaining pore space split between molten material, gas, and liquid. The number moved a little. The conclusion did not. The rest is crystalline rock, cooling and solidifying, threaded through with pockets of liquid rock and gas. Picture a sponge holding syrup instead of a swimming pool of syrup. That distinction matters because a mostly solid system does not erupt on command. It has to become far more molten than it currently is before magma could move toward the surface in any dramatic way. There's a piece of this system most people never hear about, and it changes how you should picture the whole thing. Yellowstone is not sitting still. The park itself has not moved, but the volcanic hotspot feeding it has left a trail. Roughly 16 million years ago, that hotspot sat beneath what is now the Oregon-Nevada-Idaho border. As the North American plate has slowly drifted southwest over the stationary hotspot beneath it, the site of volcanic activity has appeared to march northeast across the landscape, leaving a chain of overlapping calderas across the Snake River Plain like footprints. Yellowstone is simply the most recent footprint. In another few million years, geologists expect the hotspot's apparent position to have shifted further northeast still, toward the Absaroka Range. You are not watching a fixed bomb sitting under one unlucky patch of Wyoming. You are watching one frame of a process that has been crawling across the American West for longer than humans have existed as a species. So why does the ground rise and fall? Why do earthquakes swarm through the region by the thousands most years? This is where the story usually gets scarier than it should. The uplift and the quakes are mostly signs of a hydrothermal system breathing, not a volcano preparing to explode. Water seeps down through cracked rock, gets heated by the reservoir below, and pushes back up through geysers, hot springs, and fumaroles. Pressure builds, pressure releases. The ground swells by an inch or two, then subsides again over a period of years. Researchers at the University of Utah, who operate the seismic network that listens to Yellowstone around the clock, have recorded this rhythm for decades. It looks alarming on a graph. In practice, it is closer to the park breathing than the park exploding. But you're probably still thinking about the big one, the supervolcano eruption, the kind that shows up in disaster movies, burying Yellowstone under ash and threatening a volcanic winter across the globe. Could that actually happen? Technically, yes. Geologically, someday, almost certainly. But here is the detail that changes everything about how scared you should be right now. Timescales. Dr. Christy Till, a volcanologist at Arizona State University, studies this question using something almost nobody thinks to look at: crystals. Inside volcanic rock are tiny mineral grains that grow in rings, like a tree, recording the temperature and chemistry of the magma around them over time. By studying these crystal rings from Yellowstone's past eruptions, Till's research team found that the system can shift from mostly solid to eruption-ready in a matter of decades, not centuries. That sounds terrifying at first, but it also means scientists would very likely see the warning signs. A shift like that would show up as intense, sustained earthquake swarms, dramatic ground deformation, and changes in gas emissions, all monitored continuously by instruments already sitting on top of the caldera. Nothing like that is happening right now. The reservoir remains mostly solid. The system is not warming toward an eruptive state. It is simply doing what it has done for hundreds of thousands of years between major events. And there's another number worth sitting with. Yellowstone has had 3 enormous caldera-forming eruptions in roughly 2 million years. That is an average gap measured in hundreds of thousands of years, not decades or centuries. Statistically, the odds of a catastrophic eruption in any given year are estimated at somewhere around 1 in 730,000. You are dramatically more likely to be affected by a car accident on your drive to work than by a Yellowstone supereruption during your lifetime. That is not scientists being reassuring for the sake of tourism. It is what the data actually shows. For decades, the person who knew that data better than almost anyone was Bob Smith, a seismologist at the University of Utah who spent over 50 years studying Yellowstone's earthquakes and ground movement. Smith helped build much of the monitoring network still used today, and his long-term surveys were among the first to document the caldera's strange rising and falling behavior. What his research showed again and again was consistency. The ground moves, the earthquakes swarm, and then things settle back down. Decade after decade, the pattern repeats without ever tipping into anything resembling an eruption sequence. If Yellowstone were quietly building toward disaster, the person who spent half a century staring at its every tremor would have been among the first to see it. It helps to understand what an actual eruption sequence would look like because it is not subtle. Before Yellowstone's last major eruption 631,000 years ago, and before the ones that came before it, the geologic record shows enormous swelling of the ground, intense and sustained seismic activity, and dramatic changes in the chemistry of gases escaping the surface, all building over years or decades, not days. Modern instruments would catch every part of that buildup almost immediately. A handful of earthquakes near Old Faithful, the kind that make local news, are not evidence of that process. They are evidence of a normal, restless volcanic field doing what it has always done. So why does the myth persist? Part of it is how human brains are wired. You did not evolve to calculate probability. You evolved to notice threat. A slow, complicated geological process that unfolds over hundreds of thousands of years does not register as dangerous to the part of your mind built for spotting a predator in the grass. But a headline that says supervolcano and ticking time bomb in the same sentence lights up exactly the circuitry built to keep your ancestors alive. Fear spreads faster than nuance. It always has. None of this means Yellowstone is harmless. It absolutely has hazards worth understanding. Hydrothermal explosions, smaller and far more localized blasts caused by trapped steam flashing to vapor, happen far more often than caldera eruptions and can occur with very little warning. One such explosion carved out Yellowstone's own Mary Bay more than 13,000 years ago, and smaller versions happen on a human timescale. There is also the possibility of a lava flow eruption, similar to Hawaii's volcanoes, which is actually the more statistically likely type of future activity at Yellowstone, and far less catastrophic than the caldera-forming scenario people fixate on. Scientists monitor for all of these possibilities using seismometers, GPS stations, gas sensors, and satellite radar, all feeding data to the Yellowstone Volcano Observatory in real time. Consider what the actual monitoring network looks like on the ground. More than 40 seismometers are scattered across the region, some buried in boreholes to filter out surface noise, listening for the specific frequency signatures that distinguish routine hydrothermal shifting from the kind of harmonic tremor that signals magma actually moving. GPS stations bolted into bedrock track ground position down to a few millimeters, continuously feeding data to servers that update public maps within minutes. Gas sensors sample carbon dioxide and sulfur output at dozens of sites, because a genuine shift toward eruption would very likely change the chemistry of what is escaping the ground long before anything reached the surface explosively. None of this is hidden or classified. Anyone with an internet connection can pull up the current earthquake list, the latest ground deformation charts, and the monthly Yellowstone Volcano Observatory updates the same afternoon they're published. A system this transparent is a strange candidate for a secret countdown. Think about what that actually means for you standing in that parking lot. Underneath the boardwalks and the gift shops is a network of instruments quietly recording a conversation happening deep in the earth, translating it into numbers a scientist somewhere is reading before you've even finished your coffee. That is not the setup of a hidden disaster. It is closer to a permanent, ongoing physical exam of one of the most active landscapes on the planet, one that has been running continuously for a quarter of a century and counting. There's a reason the myth still wins, though, even against all of that data. A slow, well-monitored, statistically improbable event does not make for a good story around a campfire. Ancient humans did not survive by calmly weighing probabilities against evidence. They survived by reacting fast to anything that looked like danger, then sorting out the details later, if there was a later. That same wiring is still sitting behind your eyes right now, and it is exactly why a headline about a supervolcano under America grabs you harder than a headline about, say, coastal erosion, even though coastal erosion is actively reshaping far more of the country, far more predictably, every single year. There is something almost comforting in that, once you sit with it long enough. The fear you feel scrolling past a Yellowstone headline is not a flaw in your thinking. It is a feature that kept your ancestors alive on the savanna, tuned for a world of immediate physical threats, not slow-moving geological processes measured in 100,000-year intervals. Your brain simply was not built to feel the difference between a threat that is 5 seconds away and one that is, statistically speaking, hundreds of thousands of years away. Both get filed under danger. Both spike the same chemicals. The only difference is what you do next, whether you let that spike end the thinking or whether you use it as the reason to go looking for what the data actually says. What is genuinely remarkable, once you strip away the disaster movie framing, is how transparent the system is. Every earthquake at Yellowstone, all several thousand of them most years, gets logged and published. Every centimeter of ground deformation gets tracked by satellite. If Yellowstone were actually moving toward an eruption, it would not happen in secret. It would show up first as a dramatic acceleration in exactly the signals scientists already watch every single day, months or years before anything reached the surface. Compare Yellowstone to other places on Earth carrying the same supervolcano label, and the picture gets even less exceptional. Lake Toba in Indonesia, the Taupo volcanic zone in New Zealand, and the Campi Flegrei caldera near Naples all sit in the same category. all monitored by their own national observatories, all following the same basic pattern of long dormant stretches punctuated by rare, enormous events. None of them are erupting on any predictable clock either. Campi Flegrei, in particular, sits directly beneath a densely populated stretch of Italy, and its own scientists track the same kind of slow ground swelling that Yellowstone shows, using the same reasoning. Uplift and seismicity are baseline behavior for these systems, not proof of an impending eruption. Yellowstone is not a uniquely cursed piece of American geography. It is one of a small handful of similar systems worldwide, all being watched with the same careful, unglamorous persistence. It's worth pausing on what a worst-case eruption would actually mean, because even here the popular version overshoots the science. The most catastrophic supervolcano eruption in human memory happened not at Yellowstone, but at Toba in present-day Indonesia, roughly 74,000 years ago. For years, some researchers proposed that the Toba eruption nearly wiped out the human species, choking the planet in ash and plunging the climate into a volcanic winter that shrank our ancestors down to a few thousand survivors. It is a dramatic story, and it shows up constantly in documentaries about supervolcanoes, Yellowstone included. But more recent archaeological work, including evidence from sites in South Africa showing continuous human habitation straight through the Toba event, has pushed hard against that narrative. Humans, it turns out, are far more resilient than the bottleneck theory gave them credit for. If our species could weather the single largest volcanic eruption in the last 2 million years, the picture of instant civilizational collapse that gets attached to a hypothetical Yellowstone eruption deserves the same scrutiny. That does not mean a Yellowstone caldera eruption would be minor. Ashfall models suggest a major eruption could blanket much of the western and central United States in volcanic ash, disrupt agriculture regionally, and affect global temperatures for a period of years. It would be a genuine disaster. But disaster and extinction event are not the same word, and conflating them is exactly the kind of shortcut your brain's threat detector loves to make. The honest version of this story is dramatic enough without exaggeration. It does not need embellishment to hold your attention. It just needs the actual numbers, which are already strange enough on their own. Which brings you back to that parking lot and that inch of rising ground beneath your feet. It is not a countdown. It is closer to breathing. A slow rhythm that has been going on since long before Yellowstone became a national park, and will likely continue long after you're gone. The mountain of magma under your feet is not a bomb waiting for a spark. It is a mostly solid, slowly shifting system that geologists can watch, measure, and understand in real time, precisely because it does not keep secrets the way disaster headlines want you to believe it does. So the next time someone tells you America is sitting on a ticking time bomb, you can tell them the truth is stranger and honestly a little less dramatic. You are not standing on a bomb. You are standing on a planet that is still very much alive, breathing slowly beneath your feet, in a rhythm scientists have been listening to for decades and will keep listening to long after you leave the parking lot. There is a version of this story that would have been easier to tell you. The version with the countdown clock, the one where a single earthquake near Old Faithful means pack your bags. That version gets more views. It always has. But it also quietly teaches you to distrust the very instruments and scientists whose entire job is to give you an honest, boring, data-driven answer instead of a dramatic one. The next time a headline about Yellowstone crosses your feed, you now have something most people scrolling past it don't: the actual shape of the timescale involved, the actual state of the magma reservoir beneath the caldera, and the name of the person whose job it is to watch it every single day. None of that makes Yellowstone less remarkable. If anything, it makes it more remarkable. A landscape that has been erupting, collapsing, refilling, and rising again for over 2 million years, sitting quietly beneath a national park full of families taking photos next to boiling water, is stranger and more interesting than any countdown clock could ever be. You don't need to invent an ending for this story. Geology has already been writing one, patiently, for longer than your species has existed, and it is still writing it right now, one slow, measured inch at a time.